Hello everyone. So I'll present our recent work titled Learnable 3D Pooling for 3D-to-2D transformation of brain CT-Angiography. As a quick summary, in this work we propose Learnable 3D Pooling, L3P, which is a module that encodes 3D volumetric data into multiple 2D feature maps in a learnable way. In our method, L3P is followed by a 2D lightweight convolutional neural network to perform 3D brain image classification in an end-to-end manner, achieving equivalent results as 3D models, but with fewer parameters and lower computational cost. To introduce the topic, in the field of medical image computing, certain anatomical features and pathological conditions demand the use of 3D models to accurately capture spatial relationships and contextual information. For instance, the cerebral vasculature, consisting of a complex network of arteries, veins, and capillaries, is characterized by a highly interconnected and three-dimensional network. Contrast-enhanced imaging techniques like CT-Angiography, CTA, provide volumetric images that allow the visualization of the vascular anatomy. Here you can see axial slices of a brain CTA of a subject with acute ischemic stroke due to large vessel occlusion, LVO. The LVO, the occlusion, is located in this region here in the brain, since we do not observe contrast flowing through the arteries in this region. In healthy conditions, we would observe this area enhanced, as in the symmetrical region on the other hemisphere of the brain. But there is an occlusion, an LVO, that prevents the contrast from flowing. And as you can observe, to identify this, we need to analyze the data in its 3D space. It is very difficult to do it using only one 2D image slice. A common way of visualizing CTA images is using maximum intensity projection, MIP. The MIP technique operates by projecting the maximum intensity value along a given direction within a volume onto a 2D image plane. This process effectively compresses the 3D data into a 2D image, providing an overview of the highest intensity structures present within the volume along the specific viewing direction. In the context of CTA, MIP is particularly useful for highlighting the contrast-enhanced blood vessels, allowing clinicians to visualize the projected vascular anatomy and to identify potential abnormalities. Here you can see an example of an MIP image acquired along the axial view from this brain CTA, which corresponds to a subject with an LVO, the large vessel occlusion. And as you can see, it is quite difficult to detect the LVO from this 2D featured engineered image. So what deep learning approaches do we have to handle volumetric image data? One approach consists of using 3D convolutional neural networks, CNNs. These employ 3D learnable kernels capable to capture the volumetric spatial context. Thus, in this case, the 3D information is learned and there is no need of a task-specific design for the input. The input can be the original 3D image itself. However, compared to 2D models, 3D models have more parameters to be trained, and therefore they require more samples for training, which can be hard to obtain in the medical field. Also, analyzing and interpreting the 3D feature maps learned by 3D models is harder, since they need to be visualized using specialized 3D medical viewers or slice by slice. Alternatively, 2D models, which are computationally lighter, faster, and easier to interpret, can be applied for 3D image analysis. They can be applied either on each of the 2D slices of the 3D image, thereby capturing only intra-slice information, or they can be applied on 2D compressed renderings created from the 3D data, like, for example, the MIP. However, these featured engineered inputs require task-specific designs, which often involve manual intervention and domain expertise. Therefore, in this case, the 3D information is not automatically learned. So how can we learn and effectively compress the 3D information and also be able to use efficient 2D networks? In this work, we propose learnable 3D pooling to do so, to tackle these issues. Let's see our method in more detail. So we have the 3D input brain image, our L3P module, followed by a 2D lightweight CNN, which generates the classification output. And we said that L3P is able to automatically learn to compress the 3D info into multiple 2D feature maps. How? L3P incorporates a lightweight 3D encoder to capture the relevant 3D context information and a final unidirectional max pooling, which finally compresses the 3D information into the multiple 2D feature maps. Actually, the 3D encoder is designed to progressively compress the 3D input along one axis with end-to-end layered weights. This creates a variable number of feature maps that encode different combinations of 3D to 2D compressions regarding the weights that have been learned. This is implemented using 3 convolutional blocks that use anisotropic convolutional filters, followed by unidirectional max pooling operations, which are applied along the compression axis. In our experiments, the kernel size of both the unidirectional max pooling and the anisotropic convolution filter is 3 for the compression axis and 1 for the other axis. So for instance, if we have an input of size 4 by 4 by 3, 3 being the depth dimension, and we apply this filter of size 1 by 1 by 3, we get an output of size 4 by 4. This is how our design allows this 3D to 2D compression. And as you can see, compared to traditional 3D models, which employ 3D learnable kernels like this one here, our method has much less parameters and therefore requires less samples for training. Although our method has the potential of being versatile and applicable to various imaging modalities, in this work we apply it to 3D brain CTA classification tasks in the context of acute ischemic stroke due to large vessel occlusion, LVO. As a first thing, we wanted to see if L3P is indeed able to learn the 3D information. To do so, we designed an experiment to precisely assess the ability of L3P to encode the location of the LVO into right or left hemisphere, where the location information is actually in the compression axis, in the projection axis, which is the axis compressed by 3D to 2D transformation. So we have our 3D image and we project it into the sagittal plane. Thus, the information right or left is in the compression axis. We treat this as a feasibility experiment, since the only way to solve this is by using a projection module able to encode the 3D information. So task 1, as said, is the detection of the LVO-affected hemisphere into right or left. L3P in this case produces a multiple number of sagittal projections. And the data used in this case consists of CTAs acquired from 37 different medical sites with different image qualities and acquisition protocols. As a second task, we also tested the approach for LVO detection, also as a binary classification, presence versus absence of LVO. In this case, we chose, though, the actual view for projections, since it's the most common view utilized in the stroke context for visualization purposes. In this case, all the data comes from one only medical site. We compared our approach, a 3P-based approach, versus 2D models learning from MIP, and versus a stroke-specific 3D model. For the feasibility task, the LVO-affected hemisphere detection task here, you can see the results. For our L3P-based model, 2D models learning from a sagittal MIP, one simpler model that actually consists of the same 2D CNN used in our L3P-based approach, and a more complex 2D CNN, so as to have more parameters and be more fairly comparable to our L3P-based method. And here you can see the results for the stroke-specific 3D model. As you can observe, our method achieves equivalent results as a full 3D method. 0.96 is the 5-fold cross-validation mean AUC, while requiring much less parameters. Also, it is able to generalize well when trained using data from one medical site and tested using data from 36 different sites not seen during training nor validation. You can also see that 2D methods learning from a sagittal MIP are not able to solve the task at all. For this task, once the model was trained, our model was trained, we also wanted to inspect the intermediate outputs. Specifically, we wanted to visualize how the feature maps obtained after the L3P module looked like. So for this, for each subject, we obtained this L3P output, the 2D sagittal feature maps, for the original brain CTA and also for the flipped version of the CTA. So for each subject, we had a CTA with an LVO on the right hemisphere and a CTA with an LVO on the left hemisphere. This way we could compare the feature maps more robustly. Here you can see 3 out of the feature maps that were obtained, and some of them we observed that, like the ones with ID B and C, that they remained stable regardless the LVO location. They do not change regarding the location of the LVO. However, some other feature maps, like the one with ID A, showed statistically different densities inside the brain region depending on the location of the LVO. Thus, these discriminant feature maps are probably the ones responsible for the LVO location encoding that led to the correct prediction of this task. For the second task, here you can see the results. For our L3P-based model, we achieve, as again, equivalent results compared to a 3D model, requiring less parameters. And also, these results are statistically higher compared to a 2D model learning from an actual MIP. We also compared our method to a method found in the literature. This method is an image projection network that consists of a segmentation network that tries to encode 3D information into a 2D image plane using a projection learning module. The main differences of this method with respect to ours is that the projection learning model that they use uses only unidirectional pooling with actually larger kernel size to produce the 3D-to-2D compression. Also, their PLMs are preceded by standard 3D convolutional blocks, which use isotropic convolutional filters. Therefore, the method performs a more drastic 3D-to-2D compression and requires more parameters. Also, they evaluated their method on OCTA image segmentation, which is a task where the 3D information is helpful but not essentially, since they could already obtain satisfactory results using 2D models learning from a 2D handcrafted projected images input. And here you can see the results with respect to this method on the literature. And you can see that for the feasibility task, the detection of the LVO affected hemisphere, our method performs better, requires less parameters, and also generalizes better. And the same for the LVO detection task. Our method performs better and requires less parameters. So to conclude, in this work, we proposed L3P, a module that encodes 3D volumetric data into multiple 2D feature maps in a learnable way. We introduced the use of anisotropic convolutions coupled with unidirectional max pooling operations to do this 3D to 2D transformation in a progressive way. And we applied this method to perform 3D brain image classification, achieving results equivalent to full 3D models, but with fewer parameters and lower computational cost. And finally, you can see our code and train network weights publicly available in this GitHub repository or scanning this QR code. Thank you very much for your attention.
Thank you. Any questions? Yeah.
Thank you very much. Excellent presentation. Congratulations. My question is, did all your subjects have like the 3D CT volume, or it was just a pool of your whole sample size? And I can remember how many were those?
Let me check. Yeah, for both tasks, we used subjects that had a CTA image. So that's actually the input for both tasks. It's a CT-Angiography image. For the feasibility task, the number of data that we were working with is 449 CTAs, some with an LVO on the right hemisphere and some others with an LVO on the left hemisphere. And for the LVO detection also, we had 3D CTAs of 440 subjects, some with LVO and some others without an LVO. These were no problem.
Another question?
Nice presentation. So your model is basically taking lesser data with better accuracy, right? So this L3P is a feature extractor.
Yes.
Act as a feature extractor. So you have used a single modality, like 3D CTA images only?
Yeah. Yeah, we have applied so far to 3D CTA images. Yeah.
Okay, but there are many different kind of modality that also improve your results, like perfusion parameters, perfusion maps for this kind of task.
Do you mean? Sorry.
Okay, So CTA images is for like angiography, like
Yes.
right. So there are different modalities that that are in literature which can easily segment or
To
visualize
detect
this
the
kind of
LV or the large
veins.
vessel occlusion, you mean? There are other modalities that can be used
Yes.
for
So
detecting the large
one
vessel.
task is like having multiple modalities, and you can do the feature like that.
Yes, sure. The thing is that for this work, the main point is the method that we are proposing, which is this 3D-to-2D compression method. But for sure, this method can be applied to other modalities. I'm not sure if I'm answering your question.
Okay, we should move on. Let's thank the speaker again.